Hello all, this is Chandan Harirao presenting you about nanoscale chip design enables future Internet of Things. These presentations will contain introduction, application of Internet of Things, nanotechnology in chip design, key concepts of nanotechnology, role of nanoscale chip design in Internet of Things, enhance, nanoscale chip design for Internet of Things, recent developments, and we will wind up with the conclusion. Let's start with the introduction. IoT stands for the Internet of Things. It refers to the network of interconnected devices embedded with sensors, software, and other technologies, enabling them to collect and exchange data with each other and with centralized systems via the Internet. These devices can range from everyday objects like smartphones and wearable devices to specialized industrial equipment and smart home appliances. Application of Internet of Things. IoT has transformative potential across a wide range of sectors, including smart home, healthcare, transportation, manufacturing, agriculture, and smart cities. Nanotechnology in chip design. The benefits of nanoscale chip designs are smaller size, lower power consumption, and increased performance. Definition of nanotechnology. Nanotechnology involves the manipulation of matter at the nanoscale, typically ranging from 1 to 100 nanometers. At this scale, materials exhibit unique properties and behaviors that differ from their bulk counterparts. Nanotechnology encompasses various disciplines, including physics, chemistry, biology, and engineering, and has applications across diverse fields. Key concepts of nanotechnology. Bottom-up and top-down approaches for fabricating nanomaterials and nanostructures. Nanomaterials exhibit size-dependent properties such as increased surface area to volume ratio and quantum effects. Nanotechnology enables precise control over material properties and functionalities at the atomic and molecular levels. Role of nanoscale chip design in addressing Internet of Things challenges. There are various challenges in implementation of Internet of Things. They are bandwidth limitations, power consumption, size constraints. Security issues pose challenges for Internet of Things deployment and scalability. The nanoscale chip design solutions. Nanoscale chip design plays a crucial role in addressing these challenges by leveraging nanotechnology principles to develop smaller, more efficient, and powerful semiconductor devices. By scaling down transistor dimensions and integrating nanoscale components such as nanowires and quantum dots into chip designs, nanotechnology enables the development of high performance IoT devices with enhanced capabilities. Benefits of nanoscale chip design for IoT. The benefits of nanoscale chip design for IoTs are improved performance and efficiency of IoT devices, enhanced sensor capabilities for data collection and analysis, cost reduction through miniaturization and integration, accelerated innovation in IoT applications and services. The enhance. Energy harvesting, networked tags. Enhance are small, flexible, and energetically self-reliant devices that can be attached to objects that are traditionally not networked. Examples are books, furniture, walls, doors, toys, keys, clothing, and produce, thereby providing the infrastructure for various novel tracking applications. Examples of these applications include locating misplaced items, continuous monitoring of objects, items in a store, boxes in transit, and determining locations of disaster survivors. Nanoscale chip design for Internet of Things. Peter Kingett, a professor of electrical engineering at Columbia University, and his colleague have developed a nanoscale chip that requires so little energy in transmitting wireless signals that the batteries may never need to be replaced. Kingett's PhD student Bharadwaj Vigraham presented the chip at the IEEE International Solid State Circuit Conference and published a self-duty cycled and synchronized ultra-wideband receiver system on chip consuming 375 picojoules per bit for minus 76.5 dBm sensitivity at 2 MB per second. Nanoscale chip design for Internet of Things. The credit card size tags Kinget and his collaborators, Gil Zuzman and John Kimesis, have developed will collect energy with photovoltaic cells. The photovoltaics will draw energy from artificial light in addition to sunlight, since indoor applications are of key interest. The tags will form wireless mesh networks using ultra-wideband pulse radio wireless communications. Kinget's chip, then, is a receiver for this type of wireless communications. The unique pulse nature of the signal allows for new ways to communicate with ultra low power consumption. For example, if you wanted to communicate at a rate of 2 mbit per second, the chip sends 3 to 4 nanosecond wide pulses 500 nanoseconds apart. This means that for up to 95% of the time in between pulses, the electronics can be shut down to save power. The recent developments for their researches are the radio frequency front end consists of three stages: the LNA, which is amplifier, and stage 1 and stage 2, which consist of the receiver end. While the LNA uses inductors, stage 1 and stage 2 are realized as radio frequency G sub M C filters. A Gilbert cell self-mixer is then used to down-convert the radio frequency signal. Following this, the signal is amplified in the baseband using a VGA, and an analog demodulator is used to resolve the pulses into an RZ pulse stream. Conclusion: a dye photograph of the receiver prototype with an active area of 0.4 millimeter square, including the testing circuits, is shown in the figure. The die is 1.1 millimeter square in area and includes a ultra-wideband transmitter for testing purposes, a compact ultra-wideband receiver with a small active area of 0.44 millimeter square has been demonstrated. This receiver achieves the lowest energy consumption amongst other receivers, enabling the Internet of Things. Thank you so much for listening to the presentation.